Let me continue with what I had stopped earlier. So far it was about how to make something out of a flat sheet. Related to that was all that sheet metal work what I told you, because eventually several of the products what we make and all that have a typically a cuboid shape, and I took you through a small exercise of how to make a small unit in the workshop. There is a video and then there is a presentation. Now, I started this whole series with the understanding that with resources available to you, you can make or you can present your concept to a small group of people. You understand, no? And most times when people want to talk about any project or a product especially, they would like to say something. There you see here, this is a very well known thing. It is a one of those mouses or mice without a tail, same thing here. Only the difference you see is this one, the surface is not shiny, while the surface is shiny here, which will be a good starting point for my lecture, this particular session. The issue here is saying in real life, when you have something like this, it has a volume and you can feel something, and in contrast what you see, you can't see the volume, what you see is only the surfaces, and your brain interprets that this is the space that it is occupying, and inside it may be a solid, we can't say. And luckily for me, for purpose of demonstration, this is empty, isn't it? So, there are two very important properties associated with it. One of it is that it has an enclosed volume, then there are thicknesses everywhere, and after you have closed it, what is visible to you is only the surface and the way the surface interacts with you on a screen. So, if you see any of these CAD packages that we have, what they do is somehow they convert all these features into a some database of features. So, and when it is presented to you for you to observe, the surface characteristics are added. You understand? Now, that is how this looks different, and this looks different, and this looks different. Not long ago, just a short time back, it was considered important that these things should have a glossy finish. I can't say why, it could be a stereotype where it could be something which was not possible to be achieved, and it should feel smooth, mind the words. First time you are coming into that thing about how does it feel. In contrast, this does not appear glossy, but peculiarly it also feels smooth. So, we get into this, how does it feel in the hand. So, we have very complicated haptic interfaces by which you can hold something. Those of you who are who ever played games, and then the costlier game controllers have also a lot of hit and shake and so on like that. What does it have to do with this presentation? Why am I talking about these things? So, I suggest we just look up on the internet, though I have all of these, I thought it is a good idea. Please look here and we come into an important thing called, before we start anything, we need to learn a little bit about so called solid modeling, but the moment anybody mentions solid modeling, there are two extremes. One extreme is some people who believe that it is a little to do with sculpting and creating certain features on the screen. Good, it is correct, absolutely correct, what you say is correct, it is about creating some features on the screen. Another set of people who are especially in the engineering profession, they have come on to this thing saying a lot of it is mathematics, and quite a few of us are scared like me. And actually when you go into it, you will discuss that it is a little, life has been made simpler to us than anything else. Now looking back at this thing again, it talks a lot about 3-dimensional solids is distinguished from related areas of geometric modeling and computer graphics by emphasis on physical fidelity. When they talk about physical fidelity, how true it is to the original model that you wanted to conceive. And the principles of this geometric and solid modeling form the foundation of 3D computer aided design. So, let me sort of we come to the important aspect of why do we need to get it if it is complicated, or if it is simply made, if you can make it by hand, why not make it by hand. However, all these items, all these model making eventually should lead to a producible product. So, coming back to my this thing here, I need to produce it, I need to so represent it and make a drawing such that the people in the manufacturing setup understand. First level is somebody who can make a drawing and somebody who understands drawing. Here we seem to get into the very peculiar situation of so called engineering drawing and engineering representation. So, I will since anyway I have it in the hand, supposing I need to now show it, what we do is we hold it somewhere, and all of you must be familiar with the so called engineering drawing, in which we draw 3 views. One view looks like this, saying this is how the part would look when you look at it from here. Another view which looks like this, it shows what it is, and then yet one more view which shows how the part would look like this, and these 3 views are probably enough for the workshop person to understand. Typically this one is a, what do you call, it is not actually an ellipse, it is an elongated this thing, 2 half circles joined together. So, they will now start working on this and trying to calculate the material required. Same here. So, there are several ways. One simpler way will be, probably if I have an extrusion like this, I can look for an extrusion. And why extrusion? Extrusion in principle is hollow, and I just need to cut the extrusion to the length that is specified here. I can need to cut it to this length. Similarly, once the length is determined, the other 2 features are already taken care of. While this is a very convenient way of showing this, in reality engineering drawing has got a bad name because of okay, I will just type here, search for you on your behalf. very very interesting thing. An engineering drawing is a technical drawing used to fully and clearly define requirements for a engineered item. So, you write down something and then directly the fabricator or workshop person immediately should be able to make a part exactly as per your requirements. So, right now only talk about major features. Major features include the basic dimensions, and I am now ignoring tolerances, I am ignoring surface finishes, I am ignoring various type of fit and allowances that are required like that. And here we come to, for probably the first time, you have seen that engineering drawing is a language that communicates ideas and information from one mind to the other. So, anyway, you can look it up for that. Read it along with me. Both of them may be called simply drawing when the context is known. Engineering drawing shares some traits with drawing in that both create pictures, whereas the purpose of artistic drawing is to convey emotions. As the viewer interprets, the purpose of engineering drawing is to convey the detailed and unmistakable information to all viewers. So, when you look at an artistic presentation, you will probably think of, oh, this is what it is. It is like looking at clouds. When you look at a cloud, you can imagine various forms. In fact, I mean, there is one philosophical this thing saying a lot of us, when we imagine things, they are from the clouds. But in the case of engineering drawing, the idea is unmistakable information to all viewers. When I want a part which has to be a particular length, a particular shape, and in some procurement cases including the weight of the final component, including the characteristics of the material, and occasionally in the case of stampings including the direction of the grains which are used, and in the case of forging how things are, and in the case of castings various draft angles and various other properties and all. One of the corollaries that follow is that whereas anyone can appreciate artistic drawing, engineering drawing requires training to understand like any language. So, in fact, even my English is highly accented, except for a few people who come from the area and the same side of the river where I come from, they may have difficulty in understanding what I am talking. However, if I write something, you will know what I am writing about. It will be extremely clear, extremely objective. Engineering drawing evolved into a language that is more precise than unambiguous than natural languages, closer to a programming language in its communication ability, uses an extensive set of conventions to convey information. And if you go down, technical drawing or drafting, and not long ago means around 30-40 years back, if you looked at the title block of a drawing, designed by will be different come the drafted by, and the person who has done it. Somebody who has designed has it in his mind, somebody who has done drafting or added things are there like this, and finally it is verified. My field of engineering was mechanical, so we had to put up with a lot of drawing. I will say put up, but now I seem to enjoy it. Civil engineering people had their own this thing, saying their style of civil engineering drawings from purposes of basic civil engineering are very different, structural drawings are different, and other fabrication related to that are very, very different and they are evolved very well. Now, I will see if I can start with something. So, what has been, if I get back to what I have shown you, that part what I have shown you, usually engineering drawing usually starts with a rectangle, one more rectangle, and then what I was showing you, looks good enough, no problem. And why these have been adopted like this is, if I give a common dimension here, it looks around 20 millimeters, and this looks like 80 millimeters, and this looks like 50 millimeters. Okay, generally I have got an idea, and I now add a interesting split here. Now I know that it starts looking a little like this, and then so many other things are there. Basically we have got a idea of it. Now here comes the next problem is for a person who is operating a what I call in a machine shop. He understands setting something is easy. Even if he has to take a solid, he will look at it, and then he will one of the first thing he will start is say, I need to remove these two surfaces so that it becomes around 50 millimeters. Alternatively, he will cut both these sides, okay, to a length of 80. So we have 80, then we have 50, and then he makes everything 20. So we have a beautiful rectangular prismatic object which is of that. Next comes to how do I produce this radius. So I need to show here that what this radius is. So I indicate here saying approximately it is 10 millimeters. It is fairly complete, because normally it is understood what it is, and further often people show the center here, they show the center line, sometimes they show the center distance, but it will be redundant if I put 10 here and 50, it will be redundant. So r is equal to 10 and all that, this is sufficient for me. Now comes the slightly confusing part of it. While this is easy, anybody can easily visualize a part. The problem comes when some features which are not normal or perpendicular to the surface get represented. Now the same representations may not lead to what we are looking for. So I will give you a picture of an object which peculiarly gives I write this saying, this is how it looks from the front. I write here saying how it looks from the top. Looks sort of okay, isn't it? Now without the additional view given on one side, it is very, very difficult to understand this object. And if you, I will say examiners, I will not say they took vicarious pleasure, they would like you to point out that very peculiar results can come if we interchange a few things. So, I will make it into two parts here. I will write another feature where something looks like this from the front. If I have already seen it, you hold it, otherwise just follow my this thing. Another object again front from top. So, seemingly very peculiar things have come up here. So, if I add a side view, things will be easier. For this object, if I add a side view with an inclined plane, it is there, and then for this object the inclined plane will be different. For the present, I will just delete this, start with the other thing. Now, for convenience sake, I start here. Now, it makes sense, is not it? So, when I look from here, this is the feature we are seeing, and this is a detail about it. The only problem which we may occasionally end up is, which has comes to dimensioning earlier. For convenience, I will take something which is very easy. I will say width of this solid is 30 millimeters, and this feature is 10, this feature is 10, this feature is 10, life is solved. Similarly, height one more time, I write saying the height is 30 millimeters and this height is 10 millimeters. Looks good enough, is not it? That is how this object looks like. While it is a simple object which you can write sometime, imagine there is some other feature which is stuck on the other side. Right now, I do not know what is behind. Imagine there is some other feature which is stuck on the other side. Now, at that point, what is done is further views are given there. There is a convention which just says looking from here, draw here, looking from here, draw here, like this. Compared to several of the other things, this is a fairly simple object. Now, it sounds a little repetitive. Anyway, you can go back on the video and then check where I had started, and you will notice how these things come about. Now, I will take another solid which I had started with. Imagine this. I said this is the front view. This is the top view. So, here comes the beauty about it. It is very easy. If I just write here, I will write here and then I will proceed to the next this thing. See this, it is a solid in which a small portion is removed from there. Even here there is still a small chance of ambiguity. So, conventions have been developed which will show clearly what it is. So, if I now draw another view of it from this side, just as before, there is no way of, because this edge is not visible. So, it has come to us saying you show these edges in a dotted line. Now, if I show this dotted line, you can easily imagine this object, and more than anything the dimensioning is very easy. No dimension can be repeated, no dimension need to be interpreted. In the unlikely case that something has to be done, that you need to interpret the dimension, the whole thing to scale. So, somewhere here it will be written scale of the drawing, one whatever drawing unit here represents 10 physical units. So, if I am asking somebody to make a styrofoam box in which a small cut is there, and this typically is, let us say, something which is 100 centimeters, a meter's box with something removed, I need to make something which is small, which will fit into my screen, and then you can do it here. And while it looks okay, for convenience I have taken something like this. It is very much possible sometimes even these, there can be an inclined plane here. Imagine if there is an inclined plane here, you end up with all sorts of things when you try to draw this. But if you are to draw here, it will be very, very easy. All I have to do is show here that this is an inclined plane and give all the necessary dimensions. This can be easily produced. So, you find these partly in quizzes, partly in engineering drawing exercises. I will not call it a test. So, when you have this, you know what a modeling, what you call software is. Now, let me go back this thing where I wanted to point out now why all this is needed is that, sir, there will be field specific conventions. Just a little while back, if you remember, I was talking to you about forging, then I was talking to you about welding, I am sorry, what do you call, casting. So, in the case of casting and in the case of welding, in the case of machining, riveting and all that, generally we show the finished product. So, if I to take even a riveting assembly, a finished product does not fully adequately describe the process of making it. So, certain conventions are used here. So, again going back into the thing, sir, kindly show my hand. So, if you see, let us say two parts are being welded together like this. I will get back to a welding drawing. I have a flat and I needed to add another flat here to make it reinforced. Yes, for the few of my curious students, if you have a regular section like this, you can get it. Now, for some reason I need to add it. Let us say it is not the thing. So, several options are there. I said you can always take a section, maybe you can machine it, and it is much easier actually if you have these flats, you can do this. Now, I need to show that I need to weld these portions. Right now, this is not about the convention, but I will say, I will show something saying this is a welded portion. They have their own conventions, and more important than this, a very common thing that is used in all this is saying there is a fillet here. Because of stress concentration, because of limitations in fabrication, we need to add these two things. So, if I give a fillet radius saying is equal to 5 millimeters, while this is say 10 millimeters and this is say 12 millimeters. Now, this is fairly complete, and this is where the instructions are very, very important. And in the case of, especially in the case of welding, let me repeat, they usually write, because this seems to be very important. Once a weld is there, you should not dress a weld or should not grind it, because it is likely to create some problems. However, the person who is carrying out the job, the welder, knows how to achieve these things. So, he will try on a trial piece and then he will achieve it, and then it is not just enough if you write it as 5 millimeters. So, obviously, there is a small tolerance or allowance that is given, which is mentioned everywhere. All filleted radius should be a what do you call a minimum of say 8 mm and a maximum of 5 mm like this. So, they know how to continue the welding, and all these representations end up in a technical drawing. So, if I now go back to this thing saying these are field specific. So, if you have seen an air conditioning installation, the way they bend the pipes, the way make things is one type, and if you see the way buildings are constructed, columns and spacing of it, they have something, and these conventions and have some details that only specialist will have. I mean, he said memorized, you mean they use regularly and they can recall, they know what it means. Now, we come to something else about the important thing, saying standardization is required for specification and interpretation, also aids in internalization, because people from different countries whose can understand these languages. So, we have the IEC which has standardized several things, including how two parts fit. So, I have this is made separately, this is made separately, and anything from a bin from here can, it can take anything from a bin here and fit it. And if you say a big thing like a truck or a bus, you will be surprised that the whole drive out chassis is assembled from components that come from various parts in the world, and miraculously when they come to that place and they try to fit it, it looks as if the truck was originally assembled and it was completely knocked down and is being assembled here. The reality, it is not like this. The main ladder chassis drawings and all, at least in the case of the trucks manufactured here, I understand come from Spain, where they have a special machine where the materials are there and so on. Similarly, the various parts come from different parts in the world, and they have just mentioned it in the drawing, and it works every time. And I am sure all of you would have heard about even a huge thing like a aircraft. Various parts are made, there are specialists who do make the servos, there are specialists who make the what you call various flight instruments, and airframe people are different. And if you take typically, if you take Boeing, it comes with either you can choose a GE engine or a Pratt & Whitney engine or a Rolls Royce engine, and miraculously they all fit. You just order the engine, you can hang it. And in fact, there is an airplane which carries engines, they have a pod in which they carry an extra engine. So, if you see a picture of a aircraft with 3 engines in the front, do not get confused, they are just transporting the engine. That is the safest way and it does not create thrust. What I am trying to say is, the standardization ensure disambiguation, and we have the legal issues with it, saying you have ordered a half-inch rod or you have ordered a quarter-inch rod. A quarter-inch rod is by definition 6.35 millimeters, which is very different from a 6 millimeter rod, which is metric. And as you go down to the small sizes, for example, we have 1/8 inch sheets which are quite thicker than a 3 millimeter sheet. A 3 millimeter is very different because that is a 3.2 millimeter sheet, which is actually slightly less than that. It is you go from 25.4, 12.7, then you come to 6.35, then you come into 3.175. So, a 3.175 sheet looks a little like a 3 mm sheet, which is again different from a 3.2 mm sheet. This is where the legal requirements come inside. So, let us say you are building a car, or I have given an example of a truck. There whatever is specified is clearly it communicates all the needed information about what is wanted, and the people who will expend resources turning that idea into a reality is part of a contract. The purchase order and the drawing together, as well as any other engineering change orders, constitute the contract. So, from that point of view, this is a very, very interesting and what do you call way of conveying language. So, I will probably end this here. It is the worker or manufacturer are protected from liability as long as they have executed the conveyed in the drawing. Instructions are wrong, the fault of the engineer. So, I will now what do you call close this window, go back to solid modeling. Usually refers to the features of the solid, it is a 3-dimensional solids. In contrast, is for representing objects in the area of CAD, engineering analysis, graphics and animation, as well as prototyping and product visualization. And object is able to seen in a geographical terms as watertight. In contrast, surface model focuses more on the external aspect. So, if I now show you my mobile, which I keep carrying all around, you have seen this. It has a peculiar what you call, I do not know, a gloss about it, or pointless glids about it. I think looking at it you will know that it is definitely not gold. Then why all this is required? That is their selling point, or maybe everybody tries to copy the first successfully sold something. What you see is our surface characteristics, and this appears opaque and reflective, and this appears partly translucent. And in fact, you can even make out that there is a hole here and there is no hole here. Your eyes are able to understand this object by catching in the highlights in the corner. You see here, we have the lights get reflected here. Now you know that it is probably a thin skin, but still your eye is able to make out that what it is, and the moment if I bend it a little, the way the light changes, you know very well that it is probably a curved or flexible object. So, I will give a break here, I will continue next time saying, the starting was saying we have two things. We have a solid model. The solid model always has an enclosed volume and it inherits all the properties of the volume. So, typically a volume can have weight, typically the volume can have certain other things, saying one of the main things, if they cut the volume, it will become 2 half volumes. Got it, no? You take a cube and cut it diagonally, you get 2 wedge shaped pieces. That is the property of a solid. In contrast, a surface is only the external portion. So, if you make a nice beautiful a cube with 6 surfaces, and in fact, you must have seen the photo cubes where it is made of 2 transparent, probably acrylic parts, and then you keep all your loved ones photos and put it together, you know very well that it is hollow inside. Only the surfaces represent the object and they inherit all the properties of the surfaces. Typically, the simplest thing you can think about is the way the light reflects and the way the texture is and the way the color and various other things appear. So, the software all the time is trying to take all these geometric primitives, typical geometric primitives, which you understand, no? Simplest irreducible geometric object. So, in solid geometry we typically have cylinder, sphere, cube and so on, and you have beautiful common primitives like points, line and line segments, and then if you go down you have spheres, cubes or boxes. The one thing which is common is these planes are the ones that make all these prismatic objects. Okay. So, next time I will show you a little more about it, saying which are geometric primitives and how do you go about making a what looks like a real object, at least on the screen. And right now at the moment we are talking about simple 2D screens. Eventually you have VR, and then if you are one of the lucky people who had a chance to see Ford versus Ferrari, the 4DX animated movies, where this has been taken to an extreme. Simplest will be probably Toy Story, and the most complex is the latest 4D. So, thank you. I will continue in the next session. Thank you.